Hello everyone. In this lecture I shall discuss the power series, Taylor series and the radius of convergence. Okay. You are familiar with the power series in real variable, right? If x is a real number, then you know the power series. Now we extend this power series to complex case. Okay. So a series of the form summation an z minus z0 to the power n. Here z0 is called the center. Okay, z0 is a center, is known as a power series, and here the constants ai and the center z0, these are all complex constants. Ai and z0 are the constants. Okay, and this z is a complex variable. Z is a complex variable, that's why it is a complex power series. Okay, now you know every power series an z minus z0 to the power n is valid within a region of convergence. Okay, so we can say if summation an z minus z0 to the power n is a power series, there exists a real number r. R0 less than equal to r less than infinity. Okay, and this r is called the radius of convergence of this power series. Means suppose you are given a circle of convergence here. I say z minus z0 mode, this z0 is my center. Okay, this z minus z0 mode is less than r. So within this region the power series is convergent. Within this region the power series is always convergent. So once we write a power series, sum of the infinite number of terms with power of z minus z0, okay, so it should have a region of convergence here. So we say this power series is convergent absolutely. Suppose this is my r. So this is convergent absolutely for z mode, z minus z0 mode less than r. Means in this interior of this, right, it is convergent throughout. Now it is divergent for z minus z0 mode greater than r, right, greater than. Now here it is beyond, it is divergent, right, it is divergent here, and inside it is convergent here, right. Then no conclusion for z mode is equal to r. Z mode is equal to r means on the circle of convergence. Z mode is equal to r means on circle of convergence. Circle of convergence means on this boundary. Okay, in this boundary, right, no conclusion. We cannot say whether it is converged or it will diverge, and it is convergent uniformly for z minus z0 mode is less than some l, with 0 less than is equal to l less than here r. That means if you have a small circle here, right, we have another region here. Suppose I have another region here, and this is my L, say. Now within this region, okay, within this region it is uniformly convergent, and within this region it is uniformly convergent, and on this boundary we don't have any conclusion, no conclusion. Clear? So you know, for every power series there exists a real number r called the radius of convergence, and it is such that inside this circle it is convergent, or what we call absolutely convergent. Outside the circle it is divergent. On the boundary or on the circle of the convergence, no conclusion can be drawn. However, if we have another region inside this region, right, then we say within this small region here, this z minus z0 mode less than l is less than r, within this region, internal region, it is uniformly convergent throughout. Okay, so now before the further discussion, let me to introduce myself. Professor Susanta Kumar Paikray, currently working as a professor of mathematics at Veer Surendra University of Technology, Burla, Odisha. So without much delay, let us discuss some important remarks and followed by the radius of convergence, how to find the radius of convergence. Actually, this result is because of the Cauchy-Hadamard theorem. It is the combined effort of two mathematicians, Cauchy and mathematician Hadamard. The contribution of the joint contribution of both these mathematicians. Okay, so now we come to some important remarks. Coming to remark 1, consider the power series summation an z minus z0 to the power n with radius of convergence r. So what does it mean? That means your z minus z0 mode is less than r. Now what can you say about this r? So this r in absolute value, so r is always non-negative, r is non-negative, right, non-negative, and free from imaginary unit. Okay, free from any I, free from I, because you know a plus ib mode is what? It is s square plus b square root over, so it is free from I. So r is in absolute value, it cannot be negative and there should not be any imaginary unit in it. Okay, now my important point here is to say, now if I substitute, right, if I substitute z minus z0 to is equal to some u here, right, then what will happen to this series? Now this series becomes summation an u to the power n, or this is of the form simply an, or if I say u is my z, it is z to the power n with z mode. Okay, with z mode is my some less than r, right. Then you see here we say the center is at 0, right. Here we say the center is at 0, center at 0, right. Now you see, if you compare these two series, this and this, okay, it looks simple, right, it looks simple, right, it looks simple. So since we know any series with center at z0 can be converted of this form, right, so it is better to discuss the results in the basis of this series, and accordingly it can be extended to this. It looks simple, so we extend our study by considering the series of this form. So actually our interest is once it is convergent, this is basically the region of convergence. Okay, so we will able to write it the closed form of this series, right, we will able to write it the closed form of this series in many cases. So now, so what actually the radius of convergence? Actually the radius of convergence r is the shortest distance of z0 to the nearest singular point of f of z. So while I discuss the closed form of the series by using the Taylor series expansion or the Maclaurin series expansion, I will tell about this shortest distance of z0 to the near singular points in details later on I will tell. So now my intention is to how to find the radius of convergence. Okay, so how to find this radius of convergence? Now this radius of convergence r is limit n tends to infinity your an by an plus 1 mode, right, where this an is the coefficient. We may take this an or we may take this an, so here only the center is changed. Okay, so this, and alternatively in some cases it is here r is equal to 1 by or limit n tends to infinity 1 by nth root of an mode, right, or we may write it if I make it if I want to make it 1 by r, then it is limit n tends to infinity an plus 1 by n mod, or here r is here limit n tends to infinity nth root of modulus of an, right? In some cases, if I write this as my summation of v, summation of vn, suppose I write this is a series of this form, then, or in these cases I can say alternatively solve limit n tends to infinity vn plus 1 by vn, means the ratio of two consecutive term, the magnitude is less than 1, and if I go on simplifying, I will get a outcome of the form z minus z0 mod, okay, less than r, and this r is called the radius of convergence. This r is called the radius of convergence. So we should use this type of formula basically, and later on we will see some inspection technique to directly read what will be the radius of convergence. Now if it may happen that r is equal to 0, if r is equal to 0, then the power series has trivial point of convergence, or in such case, or we may say, or roughly we say nowhere convergence. Likewise, if r is equal to infinity, then we say then the power series converges everywhere, okay. In that way we can interpret. So here let us discuss the radius of convergence, some important series. Suppose coming to solution 1, in this case, in 1 it is of the form summation of a by b to the power n z minus z0 to the power n. This is of this form. In short, the radius of convergence here will be, by inspection, the radius of convergence r is here b by a mod to the power b by, yes, only it is b by a mod, okay, b by a mod. So that will be equal to here 2 by minus 1 mod is 2 here. It is by inspection, right? So if we want to prove it now, you see what is an, the coefficient here is this, right? This is your an. Let an is equal to minus 1 to the power n by 2 to the power n. So that means here an plus 1 is minus 1 to the power n plus 1 by 2 to the power n plus 1. If I write here 1 by r is limit n tends to infinity an plus 1 by an mod. So this is equal to limit n tends to infinity minus 1 to the power n plus 1 by 2 to the power n plus 1 into an is reverse multiplied 2 to the power n by minus 1 to the power n mod. So this is limit n tends to infinity. So this is here 2 to the power n and this. So here this cancelled, it is minus 1 mod into 1 by 2, right? So this is equal to here half, but we need here r. So therefore what is your r? R is here 2, okay. So this is 2, right? Now coming to this second question here. So the second question is solution B. In this previous question here, it is immaterial here z minus 5 or z, because z minus 5 indicates here the center here is, right? What is the center here? The center here is 5, and what it indicates? This center here is equal to here 0. This is the only difference. So now this growth of these functions can be viewed as, and one more thing, it is immaterial. n starts from 0 or 10 or 50, because convergence is decided at infinity. Okay, so this is minus 1 to the power n by 2 to the power n, and it can be viewed as z to the power n square. Okay, the growth here is like this. So instead of r, here we have the formula is r square is equal to 1 by r square is equal to limit n tends to infinity an plus 1 by an mod. Okay, in that way we will find it here 2. So that means r is equal to here root 2. R is equal to here root 2. Now coming to your question number 3. So here this growth will be viewed as z to the power n whole square. So this one is too small, we can neglect it, right? So here we can find here r square is equal to, we find in that way the answer is again here root 2, right? Answer is here root 2. So now coming to this, here the radius of convergence is here infinity, right? Now coming to E, or so coming to your D here, so let I can take this my an, right? And view of this power we will take r square, right? So coming to the solution of D, solution D, let an is equal to minus 1 to the power n by 2n plus 1 factorial. So that means an plus 1 is minus 1 to the power n plus 1, 2n plus 2 whole into n plus 1 plus 1, okay, 2n plus 3 factorial. So here r is equal to, or 1 by r, what you can write, limit n tends to infinity an by an plus 1 magnitude. You see, I am writing r. If I write 1 by r, then an plus 1 by an, the same way. So this is equal to, you can simplify it, limit n tends to infinity, here an is minus 1 to the power n by 2n plus 1 factorial, and it is reversely multiplied, and 2n plus 3 is splitted, 2n plus 3 into 2n plus 2 into 2n plus 1 factorial divided by here minus 1 to the power n into minus 1. And one more thing here, and here it will be here r square. Here r square is equal to, right? Here it will be r square. Why r square? Because the power is 2n plus 1 here, right? Because the power here is 2n plus 1 here. So if you simplify it, okay, it will simplify it, the n supersedes in the numerator here, so it is here infinity. So therefore r is equal to here infinity. Now coming to question number E. By inspection, you see, by inspection the answer should be B, here B by A mod, 1 plus I mod by 4 should be your answer. It is here root 2 by 2 into 2. So this is cancel root 2, 1 by 2 root 2 should be the answer. So you see, the radius of convergence is free from your I, because what is your an? This is your an, okay. Here 1 by r is equal to limit n tends to infinity an plus 1 by an mod. So what is your an plus 1? An plus 1 will be 4 to the power n plus 1 by 1 plus I to the power n plus 1, and an is reversely multiplied, 1 plus I to the power n by 4 to the power n, and here limit n tends to infinity. So you can write it, limit n tends to infinity, and here it is here 4 in the numerator, 4 by 1 plus I mod. So this is 4 by 1 plus I mod is root 2, right? So that will be 2 root 2. So what is your r? R is equal to 1 by 2 root 2, okay. Now coming to your solution F. Now coming to this series, so we don't bother about this plus k. This growth of this k is constant. It's small here in comparison to this, okay. So as usual, here it is here an is equal to n plus k, okay, this to the power minus 1, and this is actually here n plus k c k combination, okay, this to the power minus 1, and accordingly we will find here an plus 1 So what is equal to your an here? It is because of this inverse, it is 1 by, it is n plus k factorial, right, nck by k factorial, and n plus k minus k is n factorial, okay, in that way. So now accordingly you find an plus 1. So therefore 1 by r is equal to limit n tends to infinity an plus 1 by an mod. If you simplify it, this radius of convergence is 0. So now let me to write some standard formula for radius of convergence. By inspection we can directly tell what will be the answer. Now if the power series an z to the power n has radius of convergence r, then the power series summation an to the power k z to the power n, right, and summation n to the power k an z to the power n has radius of convergence. The radius of convergence here will be the same r, okay. Coming to 2i, however, here n to the power n, n to the power n, z to the power n, right, and here suppose some summation pn to the power n, pn is a polynomial, z to the power n, here pn is a polynomial in n, polynomial in n, or summation log pn whole to the power n, okay, z to the power n. This has the radius of convergence is here 0. The radius of convergence here is 0. Now k z to the power n, summation k z to the power n square, summation k z to the power n q, summation k z to the power factorial n. This has the radius of convergence here 1. Radius of convergence is 1 here, okay, and here the radius of convergence ROC is 0, and here the radius of convergence is 1, okay. So for short question point of view in competitive examination, you can directly apply it. Now coming to some other formula, as I have told you earlier in the example, a by b to the power n, z to the power n, the radius of convergence will be b by a, right, r is equal to b by a. Similarly, simply a to the power n, z to the power n, the radius of convergence here will be, this a will come to the denominator 1 by a, and similarly suppose it is 1 by b to the power n, z to the power n. So here the radius of b will come to the numerator, okay, b will come to the numerator, the radius of convergence will be b. Now similarly here we can say summation of an z to the power kn, right. So it has the radius of convergence r is equal to your r to the power 1 by k, r to the power 1 by k, is not it, because it can be viewed as z to the power n whole to the power k. So it can be viewed as this, right. Now if pn is a polynomial, then here pn z to the power n has the radius of convergence. Pn is a polynomial, pn is a polynomial, the radius of convergence will be here 1. Similarly, if I take the power of some k power pn, then here zn is also the radius of convergence is 1. Suppose if I can take the quotient, right, pn by qn, this polynomial I take, then here z to the power n, this has also the radius of convergence is here 1. Suppose I take pn log n, right, z to the power n, then this has also the radius of convergence 1 here, and here summation of simply log pn, right, z to the power n, the radius of convergence is also 1, and similarly summation of log pn to the power k z to the power n, it is also constant, r is here 1. Likewise, suppose it is here z to the power n by n log n to the power k z to the power n, or it is suppose summation of pn and some log of some polynomial qn by another polynomial, suppose Rn, okay, Rn, another polynomial is Rn, z to the power n, the radius of convergence is also 1. Suppose it is your an z to the power n by factorial n. Here the radius of convergence is infinity here, right? Radius of convergence is infinity here. Here a is not equal to 0. And suppose it is summation of a to the power n, z to the power k by m n, k by m n. Then it will be, for a to the power n it is 1 by a. Now this power here, so this power will be m by kth power of this. And suppose here it is a to the power mn, z to the power kn, and this radius of convergence here will be, here r is equal to 1 by a to the power, and here it is 1 by k, and here it is m, so m by k, right? So in that way. However, these are for shortcut inspection technique, but we should solve it by using the formula, okay? In complicated cases, in entrance oriented examination, this inspection method will work, otherwise this plain formula will help you. Now to conclude this lecture, I can say you have your power series an z minus z0 to the power n. You can write it of the form some an u to the power n, okay, by putting z minus z0 is your u. So that is your summation of an of the form this, of the form this. So to discuss the radius of convergence or the characteristic of this series is same as to discuss the characteristic of this series, right? Here the center is at 0 and here the center is at z0, right? And accordingly your radius of convergence we find this power series will converge, right, in a circle of, within a circle of convergence, okay? And this, it is important to find the radius of convergence, and we have shown many tricks to find the radius of convergence, right? And subsequently in the next lecture I will tell this is my z0, this is my z0. Subsequently in my next lecture I will say, while I teach you the Taylor series expansion of a function, right, an z minus z0 to the power n, this radius of convergence is nothing but, right, the shortest distance from z0 to the nearest singularity, right? It is the shortest distance from z0 to the singular point, to a singular point nearest, okay? I will tell it. So now what will be my Taylor series? My Taylor series, my upcoming discussion will be, upcoming lecture will be Taylor series, then my Lorentz series, right? The Taylor series is, means the function is analytic everywhere, it is analytic everywhere, fz is analytic everywhere, and my z0 is a point inside. Then the Taylor series expansion of fz about z0 is here f of z0 plus z minus z0 f dash z0, and so on I will tell. And in my Lorentz series I will discuss, right, if fz is not analytic at z0, right, fz is not analytic at z0, and I have a neighborhood of this z0, right, and inside this, in this annulus it is analytic, and for all z in this annulus region we can have the, right, so here it is not analytic at z0, not analytic at z0, then we have a, if it is not analytic at z0, then, but for all it is analytic at z, for all z in analytic region, we have our Lorentz series expansion, and here we have our Taylor series expansion. Fz is analytic at z0, here it is not analytic at z0, okay? Now at this stage my appeal to all of you is that if you feel this lecture is interesting and helpful, please like and subscribe to this channel, which will boost my motivation to upload subsequent lecture for your benefits. So let us close this lecture here. Thank you all.